Okay, so we are now going to work through question 6, which is all about cache locality. So this question says, consider the following kernel executing on a system with byte addressable memory. Load and store instructions operate with a 4-byte granularity. So this is just kind of saying it's word addressable. And it gives us an example program. Okay, says for this program, all the variables except the arrays out, input, and mask are mapped to registers. And then it says input starts at address 100. Mask starts at address 200, and output starts at address 400. On line 14, can you stop that, please? On line 14, the input array is accessed before the mask array. Okay, so my initial thoughts on this are, so we only have a couple lines where we're doing memory accesses. We have out here, and then we have 2 memory accesses here. We have 2 reads, and it says that this one occurs before that one. Okay, so then it says write down the memory accesses for the array accesses in the program. For example, I equals 0. Okay, so basically I have this outer for loop that is iterating from I until n. And then as a result of that, there are certain memory access patterns. Okay, so it looks like we're only considering I equals 0, I equals 1, I equals 2. So I think we can determine that n is equal to 3 then, right? Because we only access those 3. And then basically, because we're doing like this access here, and we don't want to fall outside the bounds of our array, I think what it's suggesting is it needs to check if it's less than or equal to 0 or less than n, right? Okay. So, and then at the end, we do an out access. So if we look at kind of our existing access patterns, so it tells us that in the first time we do input 0, mask 1, input 1, mask 2, and then out 0, right? So this last one is out 0, right? And then thing that kind of strikes me is like, basically each one of these accesses are going to be done in pairs, right? So this is going to be like those 2 together, those 2 together. My guess is here, these 2 are together, these 2 are together, and then the out is always at the end. So now, like that, I'm guessing that structure is going to kind of be reflected in this when we're calculating I equals 2. So to determine what happens when I equals 2, we can kind of just plug values in, right? When I equals 2, for the first, the question is, how do you know if input or mask is accessed first? It says this right here. The way that I would kind of do it is just kind of step through it. So when I is equal to 2, we just have to iterate through when j is 0, 1, and 2, right? So when j is equal to 0, so I can kind of make like a table here. So j, and I think in this column, I'm just going to compute what I plus j minus 1 is, right? So when j is 0, that gives us 2 plus 0 minus 1, which is 1. And then we go 2 and then 3, right? When I plus j minus 1 is equal to 1 and 2, right? We go ahead and perform memory accesses. But when it's equal to 3, right? This condition is triggered, right? This condition is triggered, and so we don't actually have to consider the memory accesses that occur when this happens. So we only need to consider the accesses when I plus j minus 1 is equal to 1 and 2 respectively, right? And so what memory accesses, I guess if we were just to write it in terms of the array accesses, let's kind of linearize that. So first, input at 1 is accessed, right? And that correlates to this right here. And then we do mask at j, so that's this, so mask at 0. And then we do input at 2. And then we do mask at 1, right? And then we don't do a last access because we fall into out of that if condition, right? And then at the very end, right, we need to do the output access, right? And so that's going to be out at I is equal to 2, so it's just going to be out at 2. So that's the access pattern. So now we just need to convert this into like hexadecimal addresses. So input starts at 1, right? Or input starts at 100, right? And if we want to determine the access pattern, we know that input is an array of integers, right? And so the 0th element is going to be at 100, but the first element is going to be at 100 plus the size of an integer, which is 4. So that's 104, right? So input at 1 is going to be 104. Let me do a different color. I guess, no, that's fine. So we have 104, and then mask at 0. That's going to be 200 plus 0. So just 200. By the way, it's not address 200, it's hex 200. I've messed up on exams before because I failed to differentiate those. Okay, so then we access input at 2. That is a really bad 2. And that's just going to be 108, and then mask at 1, which is going to be 204. And then lastly, we access out at 2, which is 408. Yeah. Okay. And then I'm going to go ahead and. Okay, so then it asks us for the total number of memory accesses. And that's just going to be, so in the first one I had 5, and then 7, and then 5, so it'll be 17. By the way, I'd appreciate it if you guys like double check me if you have the solutions open as I go, because I am very prone to messing these questions up. Okay. So then it says, say our processor has a fully associative cache size of 16 bytes and block size of 8 bytes with LRU. Determine hits and misses for the above program. Assume the memory address has 12 bits. Show your work. Okay, so we have a fully associative cache size of 16 and block size of 8. That means we have 2 blocks in our entire set, into our entire cache, right? And so it says determine hits and misses. So the way I like to go about this is, I think, let's just identify all the all of the addresses that belong in the same block, right? So I think I have enough colors for this. Okay, so 100 is yellow. 104 belongs to the same block because 100, if I look at like the least significant bits, the least 3 significant bits, and discount those, these belong to the same block. This belongs to the same block. This belongs to the same block. 108 does not belong to the same block, but this belongs there. This belongs there. Nope, no, that doesn't. Okay, and then if I use blue, 204 and 208 belong to the same. No, they don't. I lied. 204 and 200 do. 200 and 204 do. Yeah, okay. And then 208, 208. 108, 108. And then say I use, no, I was green, purple. And then, so now I've gone through and I've identified all of the block or all of the addresses that belong to the same block. So this will be useful, I think, moving forward. Part of that's because I was glancing at what C was, and yeah, it will be useful. Okay, so so it says, say our processor is fully associative, assume to determine the number of hits and misses. Okay, well, I guess I did that for no reason, but it'll be useful for part C. So the number of hits, so basically yellow is going to be put in, let's just go through this line by line. So yellow comes in to our cache, then blue comes into our cache. So those are both compulsory misses, right? So you get a miss, and then we get a hit, right? Because our third axis, I guess we can write it down here. We can do a miss, and then we get a hit because the yellow block was in our cache. And then we have 208, which is a green one. So that's going to be a compulsory miss. And that's also going to evict blue. Then we see purple, that's a miss. And then that's going to evict yellow. So now it's just green and purple. And then we move on to the next line. We get a miss. I'm going to fly through this really quickly. It's the same idea. So we get a miss, then we get a hit. 204 is the same block, so we get a hit. Then we get a miss. We've never seen red before. Green's been evicted, and purple's also been evicted. And then we get a miss. We get a miss. So they've both been evicted. We get a miss again. We get a hit because that was accessed recently, and then we get a miss. And so we total have 4 hits. We have 4 hits. And it was 4 out of 17, so 13 misses.
Can I ask a question?
Yeah.
Wait, so how do you know if they're still in the cache or not? Is it like, what's like a fast way to do that?
The way I was doing it is because we only have 2 blocks in our cache, right? And it's fully associative. If there was so when I'm looking at this one, if there was a yellow in the last 2, right, horizontally, then it was a hit, right? So, and when I'm looking at this, right, I'm looking at the previous 2 accesses. So I'm looking at those 2. There was no yellow in there, right? So that's how I'm determining it. I'm just looking at the last 2 accesses. The last 2 differently colored accesses, right? So when I'm looking at, so if I had 2 blues and then a red, if I had a purple, 2 blues and a red, then I would look at all 3 of those.
I see. So if the color was not in the last 2 colors, it's not in there, pretty much.
Exactly. That's the way I was kind of like, that was my brief way of like kind of flying through that. I guess it was a bit of a non-trivial thing. Yeah.
Wait, so because you have 2 blocks in the cache, when you have to evict when you get to that like third color, or
exactly. So all I'm doing in my head is I'm estimating LRU, right? So we have a fully associative cache. We have our cache only stores 2 blocks, right? And so our most recently used one is the one that was right before me, and the one before that is going to be the LRU, is going to be the least recently used, the one that's 2 colors ago, right? And so that's going to be the one that gets evicted.
And that's because there's 2 blocks.
Exactly. That's only because there's 2 blocks, right?
Thank you.
Yeah. So then looking at part C, it says, what is the minimum size of a fully associative cache with the same block size as above? same block size, okay, that can eliminate all misses except compulsory misses. Okay, so basically, if we want to eliminate all misses except compulsory misses, that means that basically I should never evict anything, or I should be able to say that once I've pulled yellow into my cache, I never have to evict yellow, right? Once I pull blue into my cache, I should never have to evict blue, right? And so the question's asking, how big does our cache have to be? So let's consider like what type of constraints that would provide, right? So looking only at, let's look at, so you see in this middle row where I equals 1, I'm gonna use a different color. Let's use white. No, let's use dark green, sure. So let's say we're looking at these two accesses, right? What is, looking only at these three accesses, right? What is the minimum cache size that we need to have, right? Well, our cache needs to be at least, 8 bytes, right? Because we need to be able to store 2 blocks. Otherwise, the 200 will evict the 100, right? So then if we look at something a little bit bigger, right? Let's say we look at, say we look at these two accesses, right? Between these two accesses, how many different colors do we look at? We look at yellow, we look at green, we look at purple. There's 3 blocks that we look at, right? And so in order for that 204 to not be evicted, in order for blue not to be evicted, there needs to be enough space for 4 different blocks, right? 4 different colors. I need to be able to store blue, yellow, green, and purple in the cache at the same time, right? And so I need to have 4 blocks in my cache, and I'd need, basically, because each block is 8 bytes large, I would need 32 bytes, right? So what I'm looking for, the reason I give these examples, is what I'm looking for is the access pattern, or basically a pair of colors, right? So a pair of blue, a pair of yellow, which have the most different colors, the most different blocks in between them, right? And so just eyeballing it, I would say that it's probably purple, right? For purple here, between this purple access and that purple access, I access yellow, I access blue, I access red, and I access green. So I access 4 different blocks, right, between these. In other words, my cache needs to be able to store 5, at least 5, to prevent any of those blocks, or to prevent purple from getting evicted, right? In order to, going back to the main idea of this question, in order to eliminate all misses except compulsory misses, I need to have no evictions, right? Or I have to have no evictions where that block is used later, right? And so what I've effectively done is I've found the longest stretch of accesses where I have the most variety of colors, which is between these 2 purples. And so essentially, I now know that my cache needs to have 5 blocks in it at minimum to minimize the number of compulsory misses. And then, so for each of these 5 blocks, each block, remember, is 8 bytes large. And so we get 40 bytes. Okay. So then the number of or really, I think it would be easier to determine the number of misses. Well, the number of misses is going to be the number of compulsory misses. And the number of compulsory misses is, we're going to have a compulsory miss for each block, so 1 for each color. And it looks like here we have yellow, blue, green, purple, red, orange. So we have 6. So we have 6 compulsory misses for 6 different blocks. And then everything else, so 17 minus 6 is going to be 11. Okay. So then it says, say you can increase the cache size to 64 bytes. What cache configuration for this increased size will result in the lowest number of cache misses? Ooh, this is a hard question. Let me think about this for a second. So what we can do is throw this out the window. Oh no, wait, I don't want to throw everything out the window. God damn it. That was the access pattern. Okay. Okay. So the way I think that you need to go about this. So we want a result. We want a cache that has the lowest number of cache misses, right? Well, if we want the lowest number of cache misses, what we need to do is we need to minimize the number of compulsory misses, right? So how do we minimize the number of compulsory misses? Well, we can assume that our associativity is fully associative, right? Sorry. Somebody corrected me. I meant capacity. What we want to do is we want to minimize the number of capacity misses, right? Because those misses are generally like the constraint, right? If we introduce new sets, right, what we're changing is we're changing which blocks are evicted, right? Which is still evictions, which is still misses. What we do is we introduce conflict misses, right? So we're going to assume that it's fully associative. So we don't introduce any conflict misses, right? And then what we want to do is we want to design our cache such that we have the minimum number of capacity misses. Well, how do we minimize capacity misses? Because you saw here that we were getting 6. So how do we get less than 6? Well, we can just make our block size bigger, right? Well, I can't make my block size infinitely large, right? So how do I know how big to make it, right? Well, the question is basically, can I make these two cache accesses in the same block? Well, for these two cache accesses, cache accessi, I don't know, cache accesses to belong in the same block, the block size would need to be, I think it would be like 2 to the 9, 2 to the 9, 2 to the 10, 2 to the 9. Regardless, it's going to be a number that is bigger than our cache. Our cache is only 2 to the 6th large, right? I can't have a block size that is bigger than that. So what that tells me is that these two addresses can't belong to the same block. Additionally, you know, anything that's in the 100 range probably isn't going to belong to the same one as the 200. 100, probably not the 400. And so what we start to realize is that that if we increase the block size such that everything within the same array, right? So all of the things in the input array, or sorry, I chose the wrong one. All the things in the input array belong to the same block. Remember, 108 used to not belong to the same block as 104 and 100, right? But what if it did, right? And same thing goes for the mask, right? What if all of these accesses, forgot about the last row here. And lastly, how can I make it so that all of these belong to that set, right? Because this will reduce the number of compulsory misses from earlier we had 6 different blocks. Now we only have 3 different blocks, right? Or 4. 1, I can't count colors. Yeah. think it's just 3. Yeah. Unless I'm, yeah, okay. So now we only have 3 different blocks, right? So how do I make my block size? Basically, I want to make it just big enough so that all of these will fit in the same block, right? Well, the block size used to be 8. And with a block size being 8, it wasn't big enough, right? We ended up getting more. But what if we doubled it, right? What if we said that the block size was 16? Well, if the block size would be 16, then 100, 104, and 108 would belong in the same thing. 200, 204, 208 would belong in the same thing. And 400, 404, 408 would belong in the same thing. So basically, that's how I got to block size being 16 bytes, right? With the block size being 16 bytes, we now only have 3 sets, or I keep saying sets, 3 blocks, right? That we're accessing. And with that, 3 blocks, 3 compulsory misses. These are all compulsory. And then the rest of them would be hits. Okay, that was a really tricky question, especially that one right there. So if you have questions, go ahead.
Can I ask a question?
Yes.
Wait, for like part D, so I guess like is the reasoning like we can't change the capacity, so we can't really reduce capacity misses because it's 64 bytes, like it has to be. And
Can you wait? Which part was this for? Sorry.
the part we just did.
Part D. Yeah.
So, like, is the reasoning like we can't really change capacity misses because it's 64 bytes, like that's just they gave it to us.
Yeah.
And to like decrease conflict misses, like we just have to make it like fully associative.
Yeah,
And
because
then
fully associative just means that there's 0. If there's fully associative, there's 0 conflict misses.
I see. And then so that means that we just need to somehow reduce compulsory misses. So the only way to, or the way to do that, or I guess the only way to do that is just to increase block size. And then so we would need to like, and then the block size can't be more than 64. And it has to be like I guess some power of 2 probably because it's like, so you just like, I guess like so you take a look at basically like which ones could possibly be in the same, I guess, block.
Yeah.
Without like,
So,
yeah.
yeah. So you're correct. The one thing I guess I kind of flew by and I didn't consider is, right, as I said, it was 16 because 8 was too small, right? And with 16, I got only 3. One other additional consideration is with 16, that means I have 4 blocks, right? And that was enough for the number of colors, right? So if your question, so I'm saying like as an extension, if somebody's question is why not 32, right? Because 32 is big enough for to make these accesses, right? Well, if I had 32, if I had my block size as 32 bytes, then I'd only have 2 blocks, right? And if I only had 2 blocks, then evictions happen, right? I start getting evictions. So that's something I didn't clarify when I was explaining it the first time. Go ahead. I'm sorry for interrupting you.
Yeah, okay, so that I guess that makes sense. So you need to find, I guess you sort of do need to try some things and like you would like I guess try, so you would know like it would be small because that's like what you had before pretty much. And you notice that 16 is fine, and then you try 32 and you realize that any more than this will get too much eviction from like, I guess would those be capacity misses?
Oh, which ones?
If you increase the block size too much, you would
If
start
you
getting,
increase if you increase the block size too much, what you start getting is you start getting capacity misses again. It's a slippery slope, but yeah.
I see. Okay. So yeah, I guess like there's not really much way but like to try. Wait,
Yeah, you sort of just gotta try. I just kind of followed my intuition because I saw that there was like a cluster of addresses that were similar to each other. And generally speaking, if we ask you this type of question, you'll be able to tell, right? Because you see that 100, 104, and 108 are really similar. So you just want to make it as small as possible around that group, right? And so the smallest possible one that I could come up with was 16. Technically speaking, if I actually want to ensure that I can optimizing it, I'd need to consider all, like 1, 2, 4, 8, 16, 32, 64, right? But following my intuition, I know that these are going to result in a bunch of them, right? So I can start kind of at 8 because I was looking at 8 earlier. And then I can look at 32 and 64, right? But my intuition should tell me that I only have one block, right? And these aren't big enough to put everything in one block. So it's definitely a little bit like you could try every configuration, but you can also, prune which configurations you're testing based off like intuition.
I see. And then wait, can you explain part C as well? Like what do you mean by like the longest stretch here? I guess like the way when I did this problem, I was just thinking how many blocks do I have? I'm gonna access 6 block or like I have 6 total blocks. So I need, 6 things. And then the last one seems to not like be used like after, so we can just -1 from that. I'm not quite sure if that works, but I feel like, or at least I have a hunch it doesn't work the way I said it, because like
Yeah.
there's like
So like,
something.
yeah, no. So that your hunch doesn't, it worked in this case, which is great. But like the reason that the logic that I was using, let me really quickly go ahead and recolor these. I'm just gonna Jesus. Okay. What was this? 104, I think. Okay, so if you remember, I had like a coloring, right? And these belong to the same one, and then that belonged to the same one, and then like these two belong to the same one. This belonged to its own, and then something like that, right? Well, the reason I was looking at the longest stretch, as I was saying, right? Basically, what I did is I considered all the pairings of sequential accesses, right? So these right here are the two closest green blocks, right? Like ignore the colors at the bottom because I haven't recolored them since I did that. But these are the two closest green blocks to each other, right? Or like they're sequential accesses to the same block, right? The same way that these two are sequential accesses to the same block, and these two are as well, right? So what I did is I considered all of these sequential accesses. In order to have no to only have compulsory misses, what I need to be able to guarantee, right, is that between these sequential accesses, the block access pattern doesn't cause an eviction, right? And so what I do, right, is looking at the small scale example right here between these two right here, right, I see that there's only one different block, one non-blue block that has been accessed between those two blocks, right? So what does that mean, right, in terms of implications for cache size, right? Well, that means that I need to be able to store at least 2 blocks. Because if I only had 1 block, right, in my entire cache, then accessing 200 would have caused an eviction, right? So that gives me a bottom bound of 1 block or of 2 blocks, right? So then if I look at a longer stretch, so let's say like my coloring, let's say that my coloring was different, okay? I'm just kind of creating an artificial example, right? Let's say my the coloring was I had black, and then I had blue, and then green, and then red, and then I had black again, right? And I say that there's no capacity or conflict misses, right? Well, for there to be no capacity or conflict misses, there must have been enough to store all 4 of these, right? For this to be a hit, right? There must have been enough room to store all 4 of these. And so the bound that I'm kind of generating is that I need to be able to store 4 blocks, right? So then what I did, right, is I here when I was kind of determining it, I found the longest stretch of colors, right? So I found in this access pattern, I found that the longest stretch between two adjacent block accesses, right? So the two closest greens were 400 and 404, right? And I found that between those two accesses, I accessed in this range, I accessed, I think it was 4 different colors, right? 4 different blocks. Well, for me not to have evicted green, for this access to be a hit, right? I need to have enough room to store those 4 blocks plus green, right? So I need to have enough room to store 5 blocks. That's how I determined 5 blocks instead of like, 6 or 4 or 3 or anything less than that. Does that make sense?
I see. And then in that case, if you don't have, so you're kind of like finding the longest stretch between accessing the same block again.
Exactly.
Where you have,
Yeah.
or like, yeah, I see. So like, what if you don't access the same block again? Can you just have a block size of, or
Well,
one
if you
block?
don't access a block again, right, you're going to get a compulsory miss, and then you don't access it again. You don't have to worry about conflict or capacity, capacity, right? So you can ignore anything that we access once.
Right.
It's
So
going to result, yeah,
you would have like one, you would just need one block or something.
yeah.
I see. Okay, that makes sense. Thank you so much.
Yep.
I
Any other
don't quite
questions?
follow. Because there's nothing that's like, so essentially you're basically saying I need 5 because of my longest stretch, which is sort of like this heuristic that we've developed about this problem. But like logically though, when you're on the last axis, like, are you saying like you can just evict, you can evict the old 400 value? And that's why it's 5 instead of 6?
1 second.
Yeah,
Just
no.
quickly write this again. 108, 204, and then let's do the coloring real quick.
Because to me, my logic was like, okay, you just count the number of unique tags that are multiples of 8, which gives you 6, which is 1 away from the actual. But I guess for some reason, there's like a optimization where we allow for yeah, that doesn't make any sense.
So, basically, the reason it's not 6, right, is, well, the reason I was able to make this optimization, right? Let's consider like the worst case. The worst case is when, let's say I had a new access. I'm going to add an access. Sure. Right. Let's say I had access 500 here. And then I had access, 501, right? So these belong to the same set, right?
Log, yep.
So in order for 501 to not be evicted, right, I need to analyze everything between these accesses, right? And between these, there's, let's see, 1, 2, 3, 4, 5, 6. Yeah, there's 6 different things, right? There's 6 colors, right? Which means that my cache needs to be big enough to store pink plus those 6 ones, right? So I'd have 7. The reason that 408 doesn't matter, right, is because when 408 comes, right, well, let's consider what the cache contains, right, when 408 comes around, right? So the cache contains, right, red, it contains blue, and like if we had, let's say we had, our cache had 5 different let's go with assumption, right, that our cache contains 5 blocks, right?
Yeah, it would hold, yeah, red, blue, purple, green, yellow.
Right. And so the reason that we can make this optimization that we don't need 6 is that at this point, we don't need purple anymore. Right?
Yeah, okay. That's
So we-
I don't know. It seems like a weird compiler optimization. Like if the program, like there's no way for the program to know that it doesn't branch back unless like it knew the future. And like
Yeah,
this
yeah.
function never, like I don't know. This seems, I think that's, I don't know, it just seems
No,
weird.
no.
I
So
don't like that.
this is definitely a contrived situation. So as somebody
Yeah,
developing an
okay.
architecture, you're never going to be given this scenario. The way these decisions are made is they just benchmark them, throw a bunch of programs at it, and they just say,
Oh,
you know,
okay.
which one's the best. This is just a kind of like a contrived. This is not something you'd kind of do in the real world. This is.
Would you say like counting the multiples of 8 is a more reasonable approach? Because I feel like that makes a lot of sense. Like you count the multiples of 8 and you don't know if they're going to be accessed again, but you know that if you're trying to minimize like the number of compulsory misses, you want to be able to hold everything in your cache because you're unbounded in the problem space.
Yes.
And the only
yes.
reason why we don't include 408 is because like, oh, we can evict everything before it because we just know that we're never going back, which is,
Yeah.
I think it's an unreasonable.
So if you had like so if you had like an unbound, let's say we framed this as a more generalized question. We weren't given all of these, right? We weren't given the addresses. Instead, we were given a situation where they told us you perform an arbitrarily long memory access pattern. Within this memory access pattern, you access 30 blocks, right? 30 different blocks. What is the minimum number of what's the minimum size of cache access, or what's the minimum size of cache that you need in order to have 0 compulsory misses? Your answer would be 30, right? Which is kind of the logic that you were
30
following,
times
right?
space size, yeah.
Exactly. But because here we are given the exact cache access pattern, we can make the slight optimization.
Yeah. Okay. That's
I
interesting.
also had a question. So is it true that if it appears just once, like if a block appears just once, we can just not include it? Like we don't need, I think like at least what I'm thinking is like you're going to need blocks to hold the number of blocks that are accessed twice. And then you kind of need to think about like if you had something that accessed once in the middle, then you need to like sort of think about like what if it will kick something and not.
What I need to consider actually is this. I need to consider all sequential pairs. I need to consider that. I need to consider this. 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 I need to consider. I need to consider that. I need to consider this. I need to consider maybe these. I need to consider. So what I need to consider is I need to consider any sequential access. I just eyeballed it and saw that purple had a really big gap between it, which is why I determined that was the longest, right? I eyeballed it. In reality, you know, if a computer was kind of doing this, the computer, like algorithmically, would need to consider every single pair of sequential accesses.
I see. So you're continuously like generating a lower bound, and the highest lower bound you get is sort of the best.
Yes. This is a tricky question. This is a very tricky question.
I see.
I think we did give substantial partial credit for people who answered 48 here. Okay, any other questions? Cool.